Monster Hunter is well known for its roster of cool and iconic monsters. While they all exemplify great creature design and fun gameplay integration, one thing that makes this gallery of critters stand out the most is the imaginative realism of it all. No matter how fantastical they may seem, most Monster Hunter monsters have a serious grounding in real biology and ecology, which informs both their place in the fictional world as well as their abilities and behavior as video game enemies. Heck, this entire channel is dedicated to exploring that depth and grounding, after all. So it is perhaps not surprising that in 2014, for the series' 10th anniversary, Capcom decided to invite 3 actual scientists to their studios and have them discuss and speculate on some of the monsters in the series. The result of that meeting was later released as Monster Hunter 10th Anniversary Super Biology Report, a celebratory booklet that features numerous short articles about a wide variety of monsters. These articles speculate on breeding behavior, biological adaptations, relations to humans, and much more, using the scientific expertise of the 3 guests. I got my hands on this booklet earlier this year and have spent some time translating it, extracting all the juicy info on Deviljho teeth that I could find, because I'm just that kind of freak, I guess. Today, I hope you're the same kind of freak, because I would like to present to you many of the ideas and concepts established in this report. Before we start, a quick word on canonicity, and it is very important to me that you understand this. These 3 guests were presumably only shown some gameplay and maybe given a paragraph of lore to read before they wrote the discussions presented in this book and in this video. They are explicitly speculating to their heart's content, and so what I'm about to tell you is not to be taken as hard canon to the Monster Hunter universe. These are fun ideas, explored through the lens of experts, not hidden lore secrets. If you like an idea presented here and choose to believe it as part of your headcanon, I couldn't and wouldn't want to stop you. Just be aware that this book is not meant to be taken as serious canon. Anyway, let's get started. The book starts with, who else? The Raths. Professor Kobayashi begins by making a few anatomical assumptions. Looking at the legs, the femur and the tibia of the Raths are essentially the same length. A leg structure like this would imply reduced mobility on land, as the leg-bone ratio seen in most terrestrial animals usually favors a length discrepancy between the bones. By comparison, Kobayashi notes that the wings are large and slender, making them ideal for long-distance flight. The bat-like structure of the wing, where bony phalange prop up a flight membrane, is considered as a sign of superior aerial mobility. He also notes that based on what they've seen from the game, the Raths seem to mostly use flight in short bursts though, which might contradict these assumptions. He also observes the Raths' head spikes, noting that they seem reminiscent of those found on Pachycephalosaurus. He theorizes that this crown serves a dual purpose, protecting the back of the neck, especially against aerial attacks, and as decorations for social interactions. The next section focuses on a fun little excursion. How might the ability to spit fire work? Kobayashi begins by emphasizing that no creature in the real world has ever been known to be able to produce and maintain fire by purely autobiological means. The major hurdle to this ability is the basic physical reality of chemistry. At maintained temperatures exceeding 45 degrees Celsius, the structural proteins vital to bodily functions begin to warp and distort, causing lethal damage rapidly. So whatever organ would be tasked with producing the flame would have to be constructed by specialized proteins resistant to heat. Then, Kobayashi describes another obstacle. We generally call the ability to spit fire, fire breath, which implies a connection to the lungs. This would make the structure extremely dangerous to the user. There would have to be specialized mechanisms to both prevent fire from entering the lungs when inhaling, and to prevent fire being produced by accident when exhaling. Considering that, Kobayashi proposes that wraths and other fire-breathing monsters might have a secondary air organ that can expel air independently of regular lung-based respiration. He closes this section by briefly discussing the Wrath's sexual dimorphism. The Rathian spends most of its time prowling the land and securing food, and as such is heavier and bulkier than her mate. Rathalos, meanwhile, spends most of its time in the air and is tasked with protecting the nest and the territory, and is much lighter and more slender as a result. The Tigrex section starts with a focus on the monster's environmental flexibility. The fact that Tigrex is repeatedly stated to not have changed much over its evolutionary history might be considered a sign that its body is already perfectly adapted to the life it leads. The Tigrex might simply not experience much selective pressure anymore. This is followed up with the question of how the Tigrex can survive in both hot deserts and snowy mountains. Kobayashi points out that Arctic regions are essentially deserts anyway. There is little rainfall and drinkable water is rare, as most of it is frozen. So many of the rules for desert survival also apply to Arctic zones. Crucially, because both sandy and snowy deserts are so harsh, they may lack large predators, with the inhabiting species specializing more on surviving the environment itself. The Tigrex may thus exploit this by venturing into both kinds of deserts to establish dominance over an unprepared food chain. All it would need for this kind of life is a body that can survive both dry heat and excessive cold, as well as excellent mobility, which the Tigrex seems to have. This section closes with one of the funniest exchanges in the book. Do you think that a Tyrannosaurus Rex could eventually develop into a Tigrex? Nope. To not leave the interviewer hanging entirely, Kobayashi muses that while there's no way that an actual T-Rex would ever evolve into anything resembling a Tigrex, their jaws are still quite similar between the two. One might consider this a kind of convergent evolution, wherein two unrelated species develop similar features to suit similar needs. Moving on to Basarios and Gravios, the booklet first discusses the Basarios' unique behavior. Why would a creature of such size and defensive ability choose to simply hide and sit still all day? Kobayashi has a possible answer. As stated by the square-cube law, when a three-dimensional body grows in size, its volume grows much faster than its surface area. So, bigger shapes have a smaller surface area relative to their volume. In living things, surface area is a key factor in temperature regulation, as that is how heat enters and leaves the body primarily. For a large creature living in hot zones such as the Basarios, this is both an advantage and a disadvantage. Heat does not easily enter the Basarios' body, insulating it against its magmatic environment. However, heat produced inside of its body also doesn't easily exit it. This makes overheating a serious threat, and so, Kobayashi argues, the Basarios adopts a lifestyle that minimizes movement. By hiding and laying around, the Basarios avoids producing heat by moving, and its natural camouflage protects it from conflict. Kobayashi observes a similar possibility with the Gravios' heat beam. To successfully live in an environment such as a volcano, a creature must be insulated against heat or have a method of expelling excess heat from the body. The Gravios' heat beam could be a form of the latter method, where firing off the laser cools down the monster by letting all the heat out at once. Professor Kobayashi compares this to sauropod dinosaurs, whose long necks and tails might also have functioned as heat-expelling mechanisms due to their surface area. The section then focuses on the monster's defensive structures. Basarios is covered in heavy, rock-like growths that likely make it too slow to actively hunt. This seems to fit with its hide-in-plain-sight lifestyle. It likely either waits for prey to get close or ambushes it by slowly coming at it unseen. By comparison, Kobayashi notes that the Gravios seems to be armored with dermal bone plates, which are probably much lighter. As a result, he imagines that the Gravios lives a much more active life. Lastly, Professor Kobayashi proposes a fun little idea. Basarios are shown in-game to eat bugs, while Gravios are said to mostly eat ores and minerals. The structures needed to digest these two food sources are quite different, however. So, he muses that the Basarios might have a traditional stomach when it's young, but might then lose that organ as it grows into a Gravios, where the stomach is replaced with organs that can then break down rock and ore. The next short section is about Barioth, and begins by describing its body. It notes that while its arms look like they could be mammalian, the arrangement of the shoulder joints caused those arms to be sprawled out to the side, a key reptilian feature, rather than pointing directly downwards as it would in most mammals. Kobayashi also takes time to point out the Barioth's tail spike, which reminds him of the Thagomizer found on Stegosaurus. He also briefly discusses childcare. In Arctic regions, it's considered more efficient to have fewer offspring and then raise them carefully to increase their survival rate. Based on that, Barioth might only produce 2 to 3 children at a time, and then nurture and parent them for a long time afterwards, similar to how polar bears handle their young. No Barioth section would be complete without discussing its iconic tusks. Kobayashi endeavors to determine who these tusks would be used against. Their length, curvature, and rigidity leads him to believe that these impressive weapons are not particularly useful against larger creatures or other rival Barioth, but are instead a key hunting feature, ideal for killing smaller prey in a single strike. Professor Kobayashi begins this part by discussing the Gigginox unusual habitat. Animals with slimy, semi-permeable skin, such as frogs, generally avoid the cold as much as possible, so to find the Gigginox in the tundra is quite odd. Kobayashi proposes that it might have an auxiliary mechanism to produce heat inside of its body, and that this mechanism requires it to sit still. This might be why it spends so much time glued to cave ceilings. This lifestyle likely causes a sluggish transition period between resting on cave ceilings and moving around. Thus, Kobayashi wonders if the Gigginox might be particularly vulnerable when startled out of its lethargic, heat-generating state. He is then asked about the Gigginox's insane reproduction rate, where it can lay a Giggisack and have its young spawn from it within seconds. Kobayashi emphasizes that there is no known creature in our world that can reproduce this rapidly, and proposes a possible explanation. The Gigginox might be viviparous, meaning that it holds its offspring within its body until they are nearly fully developed, as seen in humans. The Gigginox might be, at any given time, full of already developed Giggi that just need to be expelled through these Giggisacks. So in essence, this ability is not the Gigginox laying rapidly hatching eggs, but rather it giving birth to a pile of already developed juveniles. Next, the book discusses the way that Gigginox see. Like their relative, the Kezu, they have degenerated and presumably useless eyes. Instead, Gigginox sense their environments by sensing minute differences in temperature, allowing them to spot and track prey. Kobayashi compares it to the heat pits found in many snakes, which serve the same purpose. Lastly, Kobayashi briefly discusses the way by which Gigginox clings to walls. He assumes that Gigginox might use small hairs on their body to increase contact surface with the walls and ceilings it climbs. These structures then might work similarly to how they do in geckos, where increased surface area exploits the van der Waals principle, where small objects with enough surface area that are close to each other are attracted to each other by weak intermolecular forces. Kobayashi wonders if maybe the belly of the creature might thus be covered in these tiny hairs. The section focusing on Zinogre, the most popular monster in the series, is kickstarted by Professor Kobayashi discussing its limbs. The powerful and thick forelimbs imply great mobility, and it is assumed that the Zinogre is a fierce attacker from any angle. Yutame Mori follows this up by investigating the Zinogre's epithet, Thunderwolf Wyvern. While Zinogre certainly looks like a wolf in some aspects, its body structure and habitat do not lend itself to pack hunting and social life such as that of real wolves. Instead, Mori compares Zinogre more to a tiger, a lone predator that leaps onto its prey, pins it down, and then delivers the final blow. Next, the pair sets its eyes on the Zinogre's considerable muscle mass. Kobayashi points out that the force and agility that the Zinogre displays are abnormal, and likely contribute to an above-average success at hunting prey. Mori, however, stresses that muscles of this size and strength require an enormous amount of energy. The Zinogre's lifestyle also doesn't help. A key example of this is described in the monster's affinity for jumping. While small animals such as fleas can easily jump many times their height, the larger a creature gets, the exponentially harder jumping becomes. The leaps performed by a Zinogre thus must take an insane amount of energy and likewise necessitate continuous successful predation. But hunting may not be the only way to procure nutrients for the Zinogre. Kobayashi homes in on the Zinogre's snout and compares it to that of Spinosaurus, a controversial dinosaurian theropod that is believed to have at least partially lived in and near water. A snout like this minimizes water resistance and allows for quick lunges at underwater prey. Thus, Kobayashi wonders if Zinogre might supplement their diet with fish. Mori then moves on to talk about the Zinogre's most striking feature, its electric ability, which it derives from a symbiosis with fulgur bugs. Mori begins by theorizing how fulgur bugs may be able to produce and maintain electric charges in the first place. These critters might be utilizing ionic imbalances between their internals and the air around them to generate a weak electric charge. Being so small, a single fulgur bug can likely only produce a small charge. However, Mori theorizes that since fulgur bugs are always seen in swarms, their electric charge may in fact depend on their collaboration. By joining together, the weak charges of the individual bugs enhance each other and combine into a powerful charge held by the entire swarm. If their ability to produce electric charges depends on their ability to congregate, then their fulgur bugs would greatly benefit from a place to do so safely. That, Mori argues, is where the Zinogre comes in. Its fur serves as a perfect swarming ground for fulgur bugs, as it is easy to navigate for the bugs, but hard to access for predators. In exchange, they lend their charges to the Zinogre. But the wyvern might get even more out of the symbiosis than we previously thought. Mori proposes that since fulgur bugs glow, their main predators likely hunt them by tracking that glow. Should, for example, a gargua wander towards the glow of fulgur bugs, it might run into the Zinogre that hosts them. So, by allowing fulgur bugs to live on and around it, the Zinogre essentially sets a trap that allows him to score a few easy kills on smaller monsters that usually feed on fulgur bugs. The section on Deviljho begins with a focus on its teeth. Kobayashi points out that while mammals only ever grow 2 sets of teeth across their lives, some animals, such as sharks, are polyphyodont, meaning that they continuously regenerate teeth throughout their lives. The Deviljho seems to be one such case. This wyvern's version of polyphyodontomy reminds Kobayashi of how this concept functions in some crocodilians, where every tooth is replaced once per year. This would mean that by counting the teeth that Deviljho has pushed out of its mouth to make space for new ones, one could determine its age. So, for example, if the Deviljho has 30 tooth sockets and lives for 100 years, then it will grow a total of 3,000 teeth across its life. Next, Kobayashi is asked if he believes that cannibalism might be common in Deviljho. He replies that cannibalism is often associated with high population density, which doesn't seem to be a factor for a solitary, rare, nomadic Deviljho. He can, however, imagine that cannibalism might exist among Deviljhos as an expression of dominance, wherein large individuals might kill and feed on a smaller rival as a result of territorial aggression. Lastly, Kobayashi takes the opportunity to comment on the idea that Deviljho disrupts and destroys the natural balance. An aggressive, powerful, and voracious creature such as the Deviljho would certainly cause a lot of chaos wherever it appeared, but ultimately, the Deviljho is itself part of the natural balance. Kobayashi concludes that if the Deviljho were to destroy an ecosystem, it would likely have negative consequences for the Deviljho as well. So, there must be some mechanism to keep everything running smoothly. First, Professor Kobayashi discusses the enormous defensive abilities of the Duramboros. Its massive horns are akin to those of a bull or ram, being solid and constant, rather than needing to be shed like the antlers of a deer. Its size repels most would-be predators, but its primary defense mechanism is its durability. The Duramboros hump is like a camel's, able to store nutrients over a long period of time. This, according to Kobayashi, would enable a lifestyle where the Duramboros is unlikely to put itself in danger, as it can sustain itself with its hump. It can also likely traverse arid environments without much difficulty. Its enormous body structures might also have implications for mating behavior. Kobayashi theorizes that both the massive horns and hammertail probably evolved initially as weapons to be used against enemies and rivals. However, their current size and the decorated angles of the horns seem to have developed over time not for defense, but to attract mates. The larger the hammertail, the more intricate the horn ridges, the likelier a male Duramboros is to catch the eye of a female. Thus, to Kobayashi, this looks like a case where the initial function of a physiological adaptation has changed as the body has evolved to be more decorative. The booklet moves on to a small excursion into the ecology of 4 bird wyvern pack leaders: Velocidrome, Gendrome, Iodrome, and the Great Jaggi. Professor Kobayashi begins by pointing out that compared to most monsters in the series, these 4 are rather small. This is not a bad thing. He points to dinosaurs such as Deinonychus as examples of smaller, lighter builds being quite successful. According to him, these bird wyvern might even be able to reach running speeds of up to 50 km per hour. We next get a focus of the 4 wyverns' teeth. They are noted to be narrow, conical, identically shaped, and spaced apart. Features that Kobayashi recognizes as potential signs of a fish-based diet. He compares it to the teeth found in gharials. Kobayashi then moves on to discussing the crests of these wyvern. For the Velocidrome, Gendrome, and Iodrome, their crests grow out of the head and extend past it. These ornaments are likely entirely dedicated to social functions, such as corralling pack members and signaling dominance. The crest of the Great Jaggi, meanwhile, is a frill, similar to that of the frilled lizard. While it likely also serves a social function, Kobayashi asserts that it probably also works as an intimidation tactic and a method of temperature control. The book dedicates a pretty beefy section to Rajang, with various insights by Yutami Mori. He begins by thinking about how they reproduce. Rajang are said to be both rare and extremely territorial, which would imply a solitary lifestyle. Mori theorizes that Rajang go to severe lengths to avoid meeting another of their kind. Perhaps they mark their presence with scent and pheromone glands to ensure that any fellow Rajang avoid crossing paths with them. This is due to their territorial aggression. A meeting would immediately cause a fight, which would be to the benefit of no one. This rule is only broken during the mating season, when males and females meet up briefly to reproduce. Mori proposes that, like in many solitary species, male Rajang immediately go back to roaming the lands alone, while the females give birth and rear the children by themselves. Juvenile Rajang might stay with their mother until they themselves reach sexual maturity. Mori then wonders why no mating behavior has ever been observed. He imagines two possible scenarios. Maybe Rajang migrate to a specific, unknown location to mate. If this mating site is out of reach for other species, including humans, it would make for a safe spot and explain why they have never been witnessed in the act. Another possibility could be that Rajang have much longer lifespans than previously thought. If that were the case, their breeding seasons might be very far apart and hard to catch. Simultaneously, Mori points out that there also have been no sightings of a female Rajang with a child. This might indicate that Rajang reach sexual maturity very early and only spend a short amount of time with their mothers. Apropos of females, Mori then moves on to exploring the sexual dimorphism of Rajang. The large horns would usually be a male trait meant to help establish social and sexual dominance, and females would either have reduced or no horns. But since Rajang spend much of their time avoiding each other, it's more likely that both males and females have horns for defensive purposes. They might also serve as a warning signal to each other. The horns create a distinct silhouette that other Rajang might be able to spot from a distance and adjust their path accordingly. As for actual sexual dimorphism, Mori points at the size difference between small and large crowned Rajang, wondering if these size differences are due to gender. Moving on from monkey sex, Mori then begins discussing the habitat and lifestyle of the Rajang. Their rarity and low population density might imply that any one Rajang has a voracious need for food, so one Rajang would have to occupy a wide territory to fulfill its dietary needs. They may also either require or just prefer rare prey, which would also cause this. The actual habitats they choose are quite interesting to Mori. Being able to both live in Arctic and volcanic regions is rather special, and there could be a number of explanations for it. Mori points out that if Rajang can generate lightning, it can probably also control its internal temperature in the process by producing small currents that heat up its body. This adaptation would grant it fine temperature adjustability. On top of this basic physiological feature, Rajang might actually not need to survive in both Arctic and volcanic regions. Mori proposes that perhaps there are regional subspecies of Rajang that are adapted to their specific biome. So there might be an Arctic Rajang and a volcanic Rajang that look identical at first glance, but have subtly different body structures that facilitate life in their respective habitat. One final possibility that Mori explores is that living in these harsh climates may be a health necessity. Perhaps Rajang's immune system is particularly susceptible to certain bacteria or parasites that are commonly found in mild climates, but that die out in extreme heat or cold. So while they may be able to occasionally venture into milder areas, their extreme habitats may be a safety measure to avoid deadly infections. To close out this section, Mori turns his attention towards the Rajang's fur and its thunderous powers. Its ability to change color on the fly is quite unusual for fur, and Mori explains that for that to be possible, the hair follicle would have to rearrange the melanin pigments on it. This would mean that unlike human hair, which is made up of a living root and a dead follicle, the entire length of a Rajang hair would have to be alive, able to receive and execute signals from the body. But Mori isn't satisfied with this explanation, and proposes a more interesting hypothesis. Sometimes, polar bears that are kept in zoos located in warmer climates will turn green. This happens because the fur of polar bears isn't actually white, but translucent in a way that scatters light. Their hairs are also partially hollow, and when exposed to warmer waters, these hollow spaces become nesting grounds for microalgae, which in turn make the fur appear green. Mori theorizes that Rajang's color-changing fur might work similarly. Its dark brown coloration might be the result of bacterial colonies nesting inside of its fur, and that when the Rajang becomes excited, either an electrical or chemical signal stimulates these bacteria and their metabolism, causing them to change color rapidly in the process. Mori then takes this hypothesis one step further. If we accept that Rajang's fur is saturated with symbiotic bacteria, and its fur plays a key role in displaying its electric abilities, it could be that those bacteria play a key role in generating that electricity. Perhaps the bacteria nest on the Rajang as a means of protection, and in return grant the Rajang a small electric charge as a rent payment, similar to what happens with the Zinogre. Beyond just using the sum total of those charges as a weapon, this may also feed back into the Rajang's ability to survive in harsh environments, as its aforementioned temperature control might depend on this interaction as well. This would make the Rajang a truly amazing example of symbiotic success. Mori describes the Congalala as being highly reliant on visual and olfactory signals. The Congalala is said to accumulate a whole library of scents from the mushrooms it consumes, and these scents can either be used as weapons, such as poison gases, or as social cues for the packs that they live in. The highly decorated bodies, meanwhile, likely serve as status symbols or other hierarchical functions. Mori then moves on to the Congalala's unique body structure. A fully prehensile tail like the one it has is usually a sign of arboreal life, as are the long claws. But Congalala are not arboreal. They are firmly terrestrial, using their tail as an additional limb for grabbing food rather than branches. They can even stand on 2 feet for limited amounts of time. Mori ponders that the Congalala might have only recently evolved to life on the ground, and this adaptation began by using its tail to grab objects from the forest floor while using its arms to cling to trees. Mori, however, also notes how unusual its hands are. A core-defining feature of primates is that they have nails instead of claws, but the Congalala has long, sharp claws somewhat reminiscent of a sloth. This implies that the Congalala might have had a pretty unique evolutionary history. Next, Mori briefly discusses the Congalala's odd coloration. Pink is not a particularly good camouflage color in the jungle, but perhaps that is not where the Congalala is trying to blend in. The poison gas it emits from its mouth appears to be partially made out of small, colored aerosol particles, giving the smoke a coloration that might pair well with the Congalala's fur. So perhaps it is adapted to be able to hide well among the gas clouds it produces, instead of the trees it lives among. Lastly, Mori discusses the behavior and intelligence of the Congalala. Their ability to live in small groups and communicate via ornate decorations and distinct body language implies a significant degree of social intelligence. Mori mentions that mutual social bargaining, the ability to negotiate needs among a group, is considered key in how primate intelligence developed, and that this may show that the Congalala is on the right track. Over the coming generations, Conga colonies might even begin displaying primitive examples of culture. One key behavior Mori investigates is the Congalala's use of feces and farts as weapons. This is a known behavior in many animals, from skunks to hippos, and is often associated with an attempt to avoid direct confrontation. This might mean that Congalalas are defensive rather than aggressive, more interested in avoiding conflict than causing it. This would pair well with their ability to hide inside their own gas clouds, giving them a solid method of escape. Mori compares this to the timid yet deadly disposition of bears, and warns readers that should they ever encounter a Congalala, they should walk away slowly without turning their backs to the beast. This section focuses on the Blangonga's hunting behavior. Like the Congalala, it forms packs, but instead of bonding through decorations and social rituals, Blangonga form intimacy by hunting together and successfully executing delicate strategies. Mori describes this as another sign of high intelligence, and points out that it might even surpass that of the Congalala. Crucially, despite their life revolving around hunting and eating meat, Blangonga have flat teeth, which would imply herbivory. So what we might have here is a herbivore that has, through social structuring, unlocked the ability to hunt and devour meat. Something that is quite reminiscent of human evolution, Mori states ominously. Mori begins this section by, what else, discussing the breeding habits of Arzuros. If they are similar to bears, as implied by their appearance, then they probably live solitary lives until the breeding season, after which females take care of their offspring. However, since Arzuros live in warm environments where food is available year-round, they probably don't hibernate, and as a result, likely don't have a set breeding season. So in theory, female Arzuros with their cubs should be a somewhat common sight, as breeding can occur at any time of the year. This should be doubly true since the Arzuros seem to often venture near human settlements voluntarily, a very un-bear-like behavior. But despite this, Arzuros cubs have never been sighted. Mori wonders if this means that female Arzuros actually do perform a sort of hibernation, where they retreat into a burrow while their cubs are young. The long claws of the Arzuros are generally interpreted to serve as honey extractors from beehives, but they would also be quite useful in digging these childcare burrows, Mori argues. Moving on, the section discusses the potential evolutionary history of the Arzuros. Mori proposes that since the Arzuros probably evolved in tandem with its main food source, honey and bees, one can formulate a hypothesis regarding its body. The blue shells don't seem to serve any purpose at first glance, but one must consider that insects such as bees can see far beyond the typical visible spectrum. So, according to Mori, it's possible that the shell of the Arzuros appears blue to us, but is actually lined with various colors and patterns invisible to us but repulsive to bees. The shells on the arms might also have developed for a similar purpose. While they may initially seem to serve a direct defensive purpose against human hunters, that isn't actually the case. When the Arzuros feels threatened, it stands up on two legs, at which point its forearms are too far up and angled incorrectly to be used to deflect attacks from hunters. So instead, Mori proposes that these shells are a remnant from when the Arzuros' ancestors were much smaller. These ancestors likely still ate honey, and in order to get to it, they had to plunge their entire arms into beehives. The shells on the arms would then provide direct protection from the bees and their stingers. Mori begins by pointing out that the Lagombi might not actually be as agile as it might seem. While it is fast, its size and weight make delicate maneuvers quite difficult, which is why its speed mostly manifests as sliding in a straight line. Mori highlights that this might be why its ears are so developed, as being able to pinpoint a target accurately is vital when you can't make fine adjustments after you start moving. Mori then proposes that the Lagombi's hearing might have an even more sophisticated purpose. It is known that they store food underground, and that they are extremely good at finding stashes they buried long ago. Mori hypothesizes that the Lagombi can produce ultrasonic sounds that we can't hear, but that bounce around the environment and even underground. Like a bat's echolocation, this allows a Lagombi to map out its environment by sound alone. Moreover, by sliding on its belly, it turns its abdomen into a giant ear, as the underground echolocation can also be perceived by the exposed skin of its belly. Mori compares this to how elephants can communicate by producing low-frequency sounds that other elephants then perceive as vibrations through the soles on their feet. Mori then moves on to discuss the Lagombi's size. In accordance with Bergmann's rule, large body size is actually advantageous to living in cold environments, as a larger shape will have more volume in relation to surface area, thus being better at retaining heat. Remember the square cube law. However, most large Arctic creatures then minimize the size of any thin, external body structures such as ears to not lose additional heat. The Lagombi's massive ears, as well as its furless belly, are thus quite unusual. Mori assumes that they might have a very efficient fat insulation, which, thanks to their size, offsets any heat loss through the ears and belly. Lastly, Mori proposes a possible evolutionary history for the Lagombi. Their ancestors might have been small, bat-like creatures that heavily relied on echolocation. When they moved into Arctic regions, Bergmann's rule kicked in and their body size began to increase. But because these ancestors relied so heavily on their echolocation ability, they could not afford to reduce the size of their ears. So, natural selection favored those individuals that grew even larger, beyond what is normal, to offset heat loss from the ears and allow them to remain large and effective. It's just a hypothesis, but Mori finds that it might explain how the Lagombi can be so large while outwardly resembling a hare. Mori points out that the Kecha Wacha seems to be a mix of various creatures. Its overall appearance is reminiscent of a lemur, but the way it moves from branch to branch is more emblematic of a gibbon. Its trunk seems similar to that of a tapir, and its claws look like those of a sloth. Mori suspects that this creature had a pretty interesting evolutionary history, and begins speculating. Based on the large eyes, it's possible that Kecha Wacha's ancestors were nocturnal. Its body seems to be largely suited for arboreal life, but its size would make living in trees quite difficult. Its massive claws are obviously meant to grasp at branches, but they can also be used to walk on the ground using a knuckle gait. So, according to Mori, the Kecha Wacha's ancestors were at one point small, nocturnal, entirely arboreal creatures. They likely had large noses to help with tracking prey in the dark, and used a patagium membrane to glide between trees. As they became larger and heavier, they began spending more time on the ground, leading to the development of a quadruped knucklegate. When on land, its forelimbs were occupied, and the ancestral Kecha Wacha was in need of an extra limb. This is when the upper lip and nose of the ancestor began to fuse into a large, highly mobile trunk, able to grasp and manipulate the environment. The reason such a chaotic evolution did not result in natural selection exterminating the Kecha Wacha is likely that it also gave it many powerful adaptations. The claws and trunk are able to reach otherwise inaccessible insect nests, the size of the creature works as a deterrent to predators, and its flexible limbs allow for experimental problem solving and higher intelligence. Mori then takes the time to give advice to readers and hunters alike. When encountering a Kecha Wacha, it all depends where that encounter takes place. On the ground, the Kecha Wacha loses much of its agility, and it struggles especially with turning around. While it's still dangerous, a prudent hunter might be able to bait out an attack and then escape while the creature scrambles to readjust its body. But if you encounter a Kecha Wacha on top of a giant tree, surrounded by vines and branches, all you can do, according to Mori, is pray to God. Mori begins by asserting that the Volvidon's similarities to armored mammals such as armadillos are probably a case of convergent evolution, unrelated species developing similar bodies in response to similar environmental pressures. There is even an example for convergent evolution producing mammalian armor in the real world, pangolins, which superficially resemble armadillos but are not closely related to them. Another interesting topic is that of the Volvidon's diet. It is said to be an insectivore, but maintaining a body of such size only through insects would necessitate near constant feeding. Consider that the giant anteater, which is smaller than the Volvidon, has to eat around 30,000 insects a day to maintain its body mass. Mori proposes that the Volvidon might be employing a trick to pull this off. Insects are by themselves already highly caloric, but some become even more packed with calories right after they feed. Alteroth, for example, suck sweet nectar out of plants and are afterwards filled to the brim with energy-packed fluids. Many other insects store undigested food in their bodies to bring back to their nests. So if a Volvidon specifically targets insects that have recently fed on high energy sources, it gets the benefits of eating both the insect and those additional nutrients. This strategy could thus make an insectivore lifestyle viable even at this size. Mori also briefly theorizes on why the Volvidon's paralyzing spit doesn't affect the creature itself. The easy answer would be to simply say that the Volvidon is magically immune to it. The more interesting idea, however, is that the paralysis poison requires certain conditions to become active. Mori wonders if it might be dependent on the pH value of its surroundings. Neutral or basic pH surfaces, such as human skin, would activate the poison on contact, causing it to take effect. The inside of the Volvidon's mouth, however, might be highly acidic, thus disabling the paralyzing poison while it's in there. The section closes out with a brief word on the Volvidon's shell. Since it has to withstand the high temperatures of the Volvidon's habitat, Mori concludes that it is probably not made out of living tissue. Instead, he proposes that the shell of the Volvidon is created by secretions from the beast's skin. These secretions harden and crystallize over time, forming the protective suit of crystal armor. The production of these secretions might also be how the gases that the Volvidon emits are created. Yeah, this book even includes a section on felines. It begins with Mori trying to figure out how cats could ever develop to become bipedal. He explains that the ability to sustainably walk on two legs is a core aspect of humanity. One prerequisite to achieve this is to be plantigrade, to walk on the entire surface of the foot and thus maximize balance. This is, for example, how bears are able to briefly stand upright, as they are plantigrades. But all cats, including felines, are digitigrades, as they walk only on their toes. This would mean that the actual surface area of the feline's feet that they can use to walk on would be significantly reduced compared to plantigrade animals. Mori argues that the key must be in the joints. Palicos are able to swing huge weapons with full range of motion on their arms and wrists. So, it might be that the key adaptation that differentiates felines from regular cats is that their joints are heavily reinforced and abnormally strong. This would mean that their ankles would be powerful enough to brute force bipedalism, despite the felines being digitigrade. Other physical adaptations, such as the tail functioning as counterbalance or the spine taking a more human-like S shape, likely provide additional support. Mori then wonders how felines might have learned to communicate with humans. In humans, the emergence of linguistic communication is inextricably bound to the development of complex social structures and communities. In a sense, the ability to live in large organized groups is both the prerequisite and the result of language acquisition. Felines seem to have this part figured out, as they do in fact live in organized communities out in the wild. Mori theorizes that out of those communities came felines with above-average communication skills, which then sought out humans as a survival tactic. After all, why not ally yourself with such a prolific and successful species? Thus, the existence of humans might have propelled felines to develop language skills in an example of co-evolution. Mori is then asked a heavy question. Could mealinxes, the mischievous, non-cooperative felines that harass hunters, rise up and exterminate humanity? Mori, to his credit, takes this question quite seriously. He argues that in order for two species to engage in behavior that would lead to extermination, they would have to be competing over something, a resource or location vital to the survival of both. Mealinxes seem to live far away from humans and only bully them when they run into each other. They seem entirely independent from humans, and humans have no reason to seek out mealinxes. Thus, extermination conflicts between the two seem highly unlikely. Mori also stresses that should such a conflict happen, he'd expect humans to win. Muto begins the section on Lagiacrus by analyzing its dorsal growths. He theorizes that they are likely elongated bony lumps connected to the electricity-generating organ of the Lagiacrus. Muto, however, doesn't believe that these growths are the only factor in producing this ability. He proposes that in order to ensure the optimal condition for electric generation, the dorsal growths likely secrete a thin layer of mucus that enhances the charge and stabilizes it. It's probably this mucus that also gives these growths their luminescence, and the pulsing glow of the Lagiacrus might be a result of fluctuating densities of this mucus layer. This electric ability might not only be useful for combat though. Muto explains that a powerful tool like this would likely have many uses in order to justify the immense evolutionary cost of developing it. The thunder organ probably also works as a sensory mechanism, wherein the Lagiacrus can sense prey by detecting the electrical signals flowing through their bodies. This might be similar to how the ampullae de Lorenzini function in sharks. Muto points out that the Lagiacrus' side horns may be the detectors for this very mechanism. Next, Muto investigates the Lagiacrus' diving skills. In order for a large creature to be able to stay submerged, it must either be able to stockpile large amounts of oxygen beforehand, or have a generally low rate of oxygen consumption while underwater. Muto rules out option 1, since storing enough oxygen for something as big as a Lagiacrus would probably cause severe diving sickness. Instead, Muto points out that the Lagiacrus superficially resembles crocodilians, and so assumes that it uses a similar method to reduce oxygen consumption. A unique structure located near the heart, called the foramen of Panizza, allows crocodilians to switch their metabolism between an active and a resting mode, allowing the animal to finally control and limit its oxygen consumption while diving. The Lagiacrus's diving ability probably works similarly. Muto then mentions that a major contributor to oxygen consumption is the brain, and that more developed brains lead to a need for more oxygen. Thus, he jokingly concludes that the Lagiacrus may have an underdeveloped brain to optimize its oxygen household, and that the Leviathan might be quite dull as a result. The section then ends by briefly discussing possible natural enemies of the Lagiacrus. Muto argues that since it relies so heavily on its electrical powers, the most serious danger might be posed by parasitic microorganisms that attempt to nest on and erode the dorsal growths. Additionally, it's likely that the Lagiacrus uses the light produced by its dorsal spines as a means of communication with its peers. So if another creature could mimic this light, the Lagiacrus might be susceptible to deception and confusion, especially if it's as unintelligent as Muto suspects. Gobul holds many mysteries, and Muto starts by trying to figure out their sexual dimorphism. If the Gobul is similar to anglerfish, then male Gobul are probably quite small. This would mean that all the Gobuls we see in-game are females. Muto even wonders if the males might be parasitically attached to females, as it happens with anglerfish. Juveniles are a more complicated matter to unravel. Muto muses that Gobul might spawn in the deep sea before migrating to shallow waters, like eels. That might explain why they are never sighted in their smallest phase, as they would be deep underwater during that period. Another possibility could be that juvenile Gobul just look nothing like adult Gobul, and are thus mistaken for an entirely different species whenever they are found. Lastly, Muto imagines some of the commercial uses of caught Gobul. Like pufferfish, Gobul accumulate poison in their bodies as part of their diet, so they're likely just as difficult to prepare for consumption. The Gobul's liver might be fat and oily, and Gobul oil might make for an excellent combustible fuel source, according to Muto. The royal Ludroth is known to be the male of the species, characterized by a massive, spongy mane. Muto explains that while there are no known animals that grow spongy tissue by themselves, there are some that use sponges for symbiosis. For example, pseudospongiosaurites, sponges that are often used as shelter by hermit crabs. So perhaps the spongy mane of the Ludroth is also a case of sponge symbiosis, wherein sponge organisms attach themselves to a juvenile male Ludroth and then grow while being fused directly onto the monster. Muto theorizes that Ludroth might even have specialized neck muscles, similar to those of frilled lizards, which would allow it to move and control the mane somewhat. Muto then presents a pretty detailed hypothesis for Ludroth mating behavior, based on his knowledge of the real world. At the end of the dry season, Ludroth congregate on remote islands, far away from any predators. The male royal Ludroths arrive first, and immediately engage in territorial battles. The most dominant males divide the islands among themselves as territories, while weaker males are pushed out. Then, the female, maneless Ludroths arrive. Circling the islands, they carefully evaluate the manes and sizes of the male suitors, as well as the quality of their territories, before choosing their first mate. Any male might end up with an entire harem of females. As the breeding begins, males use the moisture in their manes to keep their partners hydrated. Shortly after, the females lay up to 4 large eggs near the shore, before getting right back to mating. This process repeats itself several times, and is subject to a lot of drama, Muto emphasizes. Females will often migrate to a different harem after a few rounds, males might clash regularly as they try to usurp another's territory and harem, and the weaker males that were pushed out before might even sneak in and attempt to secretly mate with females in another male's territory. This process is extremely taxing on everyone involved, as neither the males nor the females eat at all during this time. Once the breeding frenzy dies down, everyone rushes back into more fruitful habitats to rest, recover, and refuel with food. At the start of the rainy season, the young Ludroth hatch. These juveniles must now take to the seas and grow strong enough to be able to migrate to warmer climates once the rainy season ends. Muto concludes that a breeding strategy focusing on isolated areas such as this is efficient because it provides safety for all parties involved. Getting close to the end of the book, Muto takes on the challenge of analyzing the mighty Jhen Mohran, starting with its size. First, he notes that the Jhen Mohran's body shape is quite similar to that of a walrus. Using this and the official length measurements of the Jhen Mohran, Muto asserts that the Jhen Mohran likely weighs somewhere around 48,000 tons. That's almost 5 times the weight of the Eiffel Tower. The realization of such a large number leads Muto into a very interesting question. How does gravity work in the Monster Hunter universe? The Monster Hunter universe includes creatures of all possible sizes, ranging from completely normal to absurdly large. Muto proposes that maybe gravity is not constant in this world, and that it is instead separated into different gravity zones, some having normal Earth-like gravity, while others have much lower gravity. Low gravity zones might then allow for the evolution of enormous creatures such as the Jhen Mohran, free from the shackles of Earth gravity. Muto asserts that the entire Sand Sea might be a low gravity zone, which would explain why the sand there acts more like water, allowing the Jhen Mohran to dive easily and the sand ships to sail across the sand surface as if it were an ocean. This idea would have some serious ramifications for the entire world of Monster Hunter. Some monsters might, for example, migrate between gravity zones as they age, to take full advantage of their bodies. There may even be high gravity zones, where movement is much harder than normal. Muto wonders if hunters would use those zones as training grounds, exercising their muscles under increased gravity to develop superhuman strength. Yeah, when I said at the start of this video that you should not take anything this book says as canon, stuff like this is what I meant. This is a wild idea and really cool, but unfortunately not supported in any actual canon. Moving back to talking about Jhen Mohran specifically, Muto is asked how he would go about determining the age of such a creature. The most obvious method would be to take a cross-section of the tusk and count the rings inside it like a tree trunk. The tusks thicken at regular intervals by developing a new, distinct layer, after all. Muto, however, notes that this might not be reliable with the Jhen Mohran, as its tusks are cracked and worn down by sand. The most thorough method would probably be to mark an individual with a scar and simply observe it across time. Muto then discusses the Jhen Mohran's feeding habits. The most likely scenario, according to him, is that it seeks out underground water springs while swimming through the sand. When it senses one, the Jhen Mohran scoops up the entire spring, devouring the water and tons of sand in the process. The digestive tract of the creature is likely a cornucopia of various bacteria that are able to extract nutrients from just about anything, including all the rock and sand the beast swallows. Additionally, bacterial synthesis of the minerals naturally found in sand produces highly concentrated mixtures that the Jhen Mohran excretes through its skin, where these substances are hardened and polished by the beast's constant journey through the sand. Eventually, this leads to the surface of the monster being covered in large mineral and ore veins. This also plays into the next topic, which is the economical uses of Jhen Mohran. Muto assumes that since its body is likely saturated with symbiotic bacteria that constantly synthesize elements such as sulfur and iron, the meat of a Jhen Mohran is probably quite disgusting. The real value lies on its skin. If kept alive, a Jhen Mohran is essentially a continually regenerating source of minerals and ore. So Muto could imagine an industry focused around tracking Jhen Mohrans and routinely harvesting ores from their backs. Professor Kobayashi returns for the final section in the book, focusing on Gore and Shagaru Magala. Starting with Gore, the first feature he investigates is their blindness. Kobayashi assumes that Gore Magala must have another way to sense the world, and proposes that it senses heat signatures using specialized organs. This would likely function similarly to the heat pits found on the heads of snakes. As to why Gore Magala are blind in the first place, Kobayashi wonders if their ancestors were originally specialized to live in caves or underground. Since Gore Magalas are juveniles, maybe the species used to reproduce in the dark, where the young didn't need eyes. Moving on to the rest of the body, Kobayashi points out how bizarre it is. 6 limbs is quite unusual for such a large creature, even more so when 2 of those limbs are wings. He wonders if this may have been the result of a birth defect that entered the gene pool. The Gore's maturation process is just as bizarre. It molts, but not like lizards do, where the skin peels off to reveal a shinier but otherwise identical creature. Instead, Gore molts like an arthropod, where an outer shell is discarded and the shape of the animal can change drastically in the process. These idiosyncratic features make Kobayashi wonder if Gore Magala is, in a sense, an amalgamation of all possible forms of life. The final section asks the question of why Gore and Shagaru Magala are so rare if they are so powerful. Surely a dominant species like this would propagate far and wide, right? Kobayashi explains that in nature, there is such a thing as being too successful. The Magalas are likely indeed overwhelming forces of nature, and they probably have no trouble securing prey. But being so good at it, they probably exhaust the resources in their environment rather quickly. No prey means that the Magala population declines as it cannot support itself, which in turn allows prey populations to increase again. So the Magalas probably live on a finely balanced cycle of low and high population numbers, inversely proportional to the availability of their prey. This equilibrium seems to have settled on a small number of Magalas existing at any one time, on average. And that's it! I hope you enjoyed it. I sure did. It's probably one of my favorite additions to my collection so far. There is actually a second book like this that I discovered while making this video. It's focused on the Monster Hunter world and Iceborne monsters. So let me know if you'd like me to translate and present that in a possible part 2. Anyway, thanks for watching as always, folks. I'll see you around. As always, a special thank you to all of our patrons. I want to especially thank Ronger97, Quali, El Zendo Carlo, Matthew Chung, My Name Gone, The Dollarfish, Yamiroth, Andre, Ryan Hook, Veraxas, Thick, Kuroneko, Zion HV Augensen, AJ Rivera, Alistair, Jacob the Numbnut, Soruka, Gang Greatest, Sir Newt, EV, Rambling Robin, Black Ace 202, Dissy, Hubbo Himbro Mirror, Magenta, Danilo Villavicencio, Arcturian 711, Russell, Vulgar Beast, Person 212, Claire Miboon, Oakwood Tree, Mr. Pyramid, Makoto 2, Project Iceman, Geo, Jamie Tate, Nils Schlatter, Iron Camel, and I'm going to bed. Take care, everyone. Thank you, as always, for your support.